Okay, everybody, so let's look at doing some of these trig problems where we left off today. So in my notebook, I'm on page 19, and there's nothing to tape in. These are all just going to be regular old notes. Okay? All right, so the first thing that we're trying to do is direct substitution. And anytime that we're working with trig, if we can do direct substitution, that's good. Okay, so when you see a problem like this, so one of the things I know from pre-calculus is that students aren't very comfortable with that. And so I want you to make a note that, that the sine squared of theta is the same as the sine of theta squared. Okay? So let's look then at this problem. Okay, so the limit as theta approaches pi over 2 of 3 sine squared theta is equal to, I'm doing my direct substitution, so I'm dropping off the limit, 3 times the sine of pi over 2 squared. Okay, well, the sine of pi over 2 would be 1. So there's our answer. Okay, and that's kind of the extent of when we talk about like that we have to make sure that we know our unit circle, that you're going to see very common ones. So you want to make sure you're pretty quick at that. Okay, so if we can use direct substitution and it works, great. But what happens if we get that indeterminate form and direct substitution isn't going to work? Well, the next thing we can do is we can rewrite the function using trig identities. And somebody mentioned that today. Okay, so, oops, let's do an example. So let's say that we have the limit as theta approaches pi over 2 of 2 cosine theta cotangent theta. Okay. So hopefully this is ringing a bell here, because how can we simplify this? Or maybe even in this case, we're not going to get the indeterminate form, but it's just a drag working with cotangent. I don't want to figure out the cotangent of pi over 2. So I could just rewrite this, and I could say, well, cotangent is cosine over sine. So again, let's just look at ways that we can manipulate this. Okay, so we have cosine times cosine, which is 2 cosine squared theta over sine theta. And that's just a friendlier thing for my brain. Okay, so I'm going to go ahead and I'm going to go back here and say, all right, I'm going to put my limit here. Because remember, we have to be watching our notation. Now I'm going to do my direct substitution on the next step. Okay, so I have 2 cosine pi over 2 squared over the sine of pi over 2. Okay, well, we know cosine of pi over 2. Again, I'm just thinking pi over 2 is right here. Cosine would be 0. So this is going to be 0, because anything times 0 is 0. Sine of pi over 2 is 1. And that would be 0. Okay, so anytime, if I can work in sines and cosines, I just find that a lot easier. Okay. And if I'm going too fast, just pause the video. Like you guys wouldn't have figured that out. Sorry. Okay, so let's say we have sine theta cosecant theta over 3 theta. So again, I might not get the indeterminate form, but I don't really like dealing with cosecant. So I'm going to rewrite this. So cosecant, remember, is 1 over sine. So it's going to look like that. So our sines are going to go away. So I'm going to have the limit as theta approaches pi, so right, those are gone, of 1 over 3 theta. So I always want to show, like, once I've done some algebra work, I've done some algebra work right here, but I'm going to show, okay, here's my simplified version. Now I'm going to go to my problem, and this is equal to, I'm going to put in my direct substitution, and there it is. Okay. Okay, so what we're going to see when we're working with the trig functions is that these behave just like other functions. Let me find a ruler here. As far as, well, what are the things that could happen when we're doing this? Okay, so, sorry, I thought this was done already. I'll start with that there. Okay, so one of 3 things is going to happen. So you're either going to get a number. So you try direct substitution, and you get a number. Yay, we're happy. We don't have to do anything. Okay, maybe what you'll do is you'll get a number divided by 0. Okay, if you do direct substitution and a number divided by 0, then we say the limit does not exist. Okay, that's kind of nice too, because we don't have to do anything. Okay, the other thing is that we're going to get 0 over 0. And remember, that is the indeterminate form. And we talk about what you should do is you should inspect one-sided limits. And I'm just going to leave this right here as just some directions. I'm going to show you guys like another technique that we can use, or some other things that we can use, and then we'll do a bunch of examples of, as I'm looking at my notes here. I'm thinking this isn't going to come up for a little bit. So for right now, I just want you to know that we have these 3 things that could possibly happen. Okay, so we have some special trig limits. And that's going to be the first way that we're going to deal with this. So what happens is that we have some limits that we use a lot, and we're just going to memorize them. And we can't prove them yet because we don't know enough calculus. So they're ones that we're going to just kind of look at the graph and we're going to go, okay, graphically, here's what's happening, and we're just going to accept that. Normally in calculus, you can't prove anything with a graph. Like we started working with limits with graphs just so that we understood the concept of what was happening. But we always are going to have to do things algebraically. Okay, so for now, I want you to memorize these. Okay, and just know that we will learn. We have this thing called L'Hopital's rule. And we won't learn about L'Hopital's rule for a very long time. And, well, maybe, I shouldn't say very long. it kind of looks like L Hospitals rule, but you say l'hôpital. So once we have to know a lot more calculus in order to use this rule to help us actually figure out these special trig limits. So for now, let's just look at their graphs. Okay, so one that's super important is the sine of theta over theta as theta approaches 0. Okay, well, if we did direct substitution, the sine of 0 is 0. And then 0 over 0 would be that indeterminate form. And we would have something much later on that we can prove it. But for now, what I want you to note is that there's a hole in the graph right here. And it kind of looks something like that. Okay? So that's why it was that indeterminate form. And we can't show the hole like we did with rational functions. Okay, so in this case, this number right here where there's a hole, this is at 1. So I want you to memorize, because this is going to come in handy, that the limit as theta approaches 0 of the sine of theta over theta is 1. And you'll see that eventually we're going to have a lot of functions put together, and we're going to like break them up into little pieces. And if we could break it up into that little piece, well, we know that little answer there. Okay, the other one that is very important as far as it comes up quite a bit when we're simplifying is 1 minus the cosine of theta over theta. So you can see that if we put a 0 in there, well, the cosine of 0 is 1. So I would have 1 minus 1, 0 over 0, indeterminate form. So we're going to just look at the graph. And this graph has a hole, like right at the origin there. And we're not really that interested in what the graph looks like. I just want you to know it's something like that. So as we're coming to 0 from the left and the right, we're headed to 0. So we're going to know that the limit as theta approaches 0 of 1 minus the cosine of theta over theta is equal to 0. So for me, when I memorize these, it works better for me to memorize the graph, because otherwise I'm constantly going, wait, is this the one that's 0 or is this the one that's 1? So it's helpful to memorize the graph. Also because we also start talking later on about, well, what's this graph doing as we're going out to infinity? And so it's just helpful if you have just a general idea of what the graph looks like. Okay, so this is basically, it's like the same rule, or it seems similar to it, but you'll notice that sometimes we write it this way and sometimes we write it this way. And it's really confusing for students because it's different. Okay, so this one down here, it's like the same graph. All it is reflected. So it's kind of going like this and like this. And it's also got a hole right here at 0. Maybe I should put that. Okay, so we want to know that the limit as theta approaches 0 of the cosine of theta minus 1 over theta is equal to 0. Okay, so these are going to be 3 special trig limits that we can't prove just yet, but they're going to be very helpful for us when we're solving future problems. Okay, that's going to be the end of part 1.